Okay, so finally, now that we have this analysis of a particle in a box, which is a toy model or simplified model for an atom, for the states of an electron in an atom. Now let's see how we can use this to implement qubits. Okay, so remember our model had the particle in the box, and we solved Schrödinger's equation for a free particle, which was confined with these boundary conditions that psi of 0 equal to psi of L equal to 0. And then we got this quantized solution. So first of all, we saw where this quantization of energy comes from. It comes from the fact that the stationary states of the electron, the states of constant energy, are these the eigenstates of H, and they are standing waves in this interval, and they happen to have these quantized energies which vary as n squared. So they are numbered n equal to 1. The states are numbered n equal to 1, 2, 3, and so on. The energy of the nth state is proportional to n squared, and the corresponding the nth state has n nodes in it. It has these. Okay. So now, how do we use this to implement a qubit? Well, what we could do is make sure that our electron has energy at most E sub 3. It has energy strictly less than E sub 3. Right? And so now, if it has energy strictly less than E sub 3, it's confined to be in one of these two energy levels, 1 or 2. Okay, so we can confine it to have low energy, and we can call this n equal to 1 state the 0 state, and the n equal to 2 state the 1 state. Right? And so in general, our electron will be in a superposition of 0 and 1, and so we'd have implemented a qubit. So let's look at this more carefully. So we've made our total energy much smaller than E3, so that we want it to be in a superposition of just these two eigenstates of H, which we call the 0 and 1 state. And then in general, of course, we are in a superposition of the two, and so we'd be in some superposition alpha times the 0 state plus beta times the 1 state. The 0 state is psi 1, which is of course it's a continuous state, quantum state, right? And it's given by this particular superposition. Its wave function is this normalization times sine pi x over L. And similarly, the 1 qubit state is given by this normalization times sine 2 pi x over L. And now, as we let this state evolve in time, of course, this first part of the superposition is going to precess at a rate proportional to E1, and the second one will precess 4 times as fast because it's at a rate proportional to E2. And if we factor out this precession due to E1, so we could look at the qubit in a rotating, frame, then still you have a relative rotation which is proportional to E2 minus E1. Right? So if we call this delta E, which is E2 minus E1, for the hydrogen atom, this is about 10 electron volts. And if you look at the corresponding frequency, which is this divided by H, it's about, the frequency is about 2.5 times 10 to the 15 hertz. Okay, so this this frequency turns out to be very close to the frequency of optical light. So this is why you can actually control these atomic qubits by optically, by through interaction with light pulses. Okay, so this gives us our implementation of a qubit atomically, as well as suggests how one actually implements gates, and those are done by very precise light pulses directed at this qubit.